morning, everybody. My name is Lorne. I'm a chief technologist with Mercury Systems. I need to give you guys a little bit of background. I'm not kind of a digital processing guy. I'm more of an RF analog guy, a systems engineer. So I feel like a little bit of a fish out of water talking about some of these things, right? But what I really wanted to talk about was a new kind of innovation in changing closed design and integration practices in the RF sensor chain, right? So it's really about how do you start a new paradigm, right? So how do you start a new paradigm? Sometimes you have to go all the way back to the roots, even the roots of what actually brought us to being engineers to begin with, right? So how many of you in here played with Legos as a kid, right? Exactly, everybody, right? I still love playing Legos with my son, right? You know, we built the next great fighter jet this past weekend, as a matter of fact, right? So the Lego building block approach has worked wonderful in the digital domain, right? Started with some of the VME chassis, and with the advent of OpenVPX, it's been magnificent, right? You don't think about it, but let's say you just want to augment or offload a function in VPX, right? When you do that, you sometimes just simply add in a GPU. You may add in an FPGA coprocessor, but you're just simply offloading a function, and the interoperability of like something like OpenVPX has allowed us to do that pretty much seamlessly, right? I'd challenge any of you to go ask an RF systems engineer to change out or add just augment capabilities in his system, right? You better have your medical team with you because he's going to have a stroke on the spot. And that's the truth, right? So how do we get to that, right? At some point, we have to change that paradigm. But first, you got to kind of understand, why is RF always so custom, right? So you think about it, RF comes from a standpoint of where people look at a big, broad spectrum, and they isolate down to a custom point, a custom solution. If you think about it, almost everybody in this room has a embedded RF digital subsystem probably carrying them around. We have one left up on the stage a minute ago, right? All these phones everywhere. That's exactly what they are, right? But RF guys, I mean, there is some validity to their concerns, right? So they're worried about phase noise all the time. They're worried about isolation. They're worried about noise immunity. I mean, think about it. Those guys are even worried about the distance their circuitry is away from the shields that they keep on the board to keep the digital noise out, right? But the real problem in all this custom circuitry in embedded world, and especially in military embedded applications, is at some point you have to go get your RF witch doctor to come in and somehow make this RF work. And that's really the truth. Every company seems to have somebody like that that can come in and finally get an RF system to work. RF systems are notoriously take a long time to deploy, and somehow we have to get away from that framework. So just think if we had an RF receiver that was a red Lego, a transmitter that's a blue Lego, a synthesizer that's a green Lego, and we could just grab them and pull them and plug them all together and build a system out of them, right? So what would you need to do kind of an open systems architecture framework like that, right? In the RF domain, one of the things you're going to need, you need some type of common, building block module for the RF. You're going to need some type of software or middleware layer to abstract RF control out to all the various, protocol type command control, gigabit Ethernet, PCI Express, whatever that may be. You still have to be able to handle all of the RF control through all these various different protocols, right? And lastly, you got to be able to scale, right? So you got to be able to scale from one form factor to another, and even all the way out sometimes to, I call them semi-custom, but a distributed aperture architecture, where you may have conforming antennas in the wings of a UAV or in the wings of a plane, and you want to be able to put your RF equipment right beside that so that you can then go to a centralized processing system, right? So that's kind of the framework for it. There is a framework we have today. It's called OpenRFM. You see it listed at the top up there. What OpenRFM is it defines a common volume, electrical connectivity, and power for RF modules. And then below that is a layer of software and hardware that creates an abstraction layer that allows you to have your RF controls basically abstracted away from any of the control planes that you have, whether it's PCI Express, gigabit Ethernet, serial rapid I/O, doesn't matter, right? And then that allows you to be able to scale that quickly and easily if the volume's defined correctly from 6U VPX to 3U VPX. And even more importantly, it can retrofit back into older systems that still rely on VME, that don't need that processing uplift. They've had it for years, but they've never been able to upgrade the RF. This gives that capability. So OpenRFM is very similar to what OpenVPX was trying to accomplish. Complete interoperability between the RF building blocks and the digital building blocks that are in these systems, right? So that's why you see me kind of in all these slides talking about the Lego building block approach, because that's really what it needs to be. We need to be able to pick the same digital and RF components from multiple systems and just slide them across. So this is just kind of an example of how you would do various systems with this open systems architecture approach to RF, right? So let's say you have a surface warship, a large platform like a B-1 bomber, B-2 bomber, and you're going to upgrade an EW system in it or completely add a new one, right? So at the same time, you've got a small form factor or a small platform like a UAV or even an unmanned underwater vehicle, and you want to do an electronic warfare upgrade to it as well for self-protection, right? So the same system that builds a very comprehensive electronic countermeasure system on a warship, those same exact building blocks are used to build a small self-protection system that are used on a UAV or a UUV, right? So what you can actually do is take this same common IP that you know works, it's completely interoperable, and you just configure the building blocks slightly, and now you've got what was a very large 6U based VPX type chassis in the bigger platforms. You've scaled it to a 3U VPX chassis, and it's the exact same RF equipment, right? It's proven technology, right? That's where RF systems engineers then start to go, aha, I really like this because now I can rely on what I've proven in a big ship and port it over to my UAVs, right? It gives commonality across that. And you might think, okay, well, that's great, Lorne. All sounds wonderful, right? But why would you want to do that, right? Why? So we all know budgets in the DoD are shrinking, right? Budgets are simply going down, and it's going to be that way for quite some time. But the threats are going up astronomically. And not only are the threats increasing in number, they're able to adapt at quite frankly, an alarming rate for those of you that have seen EW in the last few years. So we have to come up with something that is interoperable, it's got to be scalable, it's got to be flexible, and most of all, it's got to be affordable, right? So using these common building blocks, just like we do in the digital domain, we do that in the RF domain, and we've hit that affordability, scalability, and we've added agility to our EW subsystems, right? So it's not just my way of thinking. I wanted to read a quote to you guys. That's why I brought the papers up here, since I didn't want to remember these big long quotes. In 2013, the electromagnetic spectrum strategy was put out by who now is nominee for Secretary of Defense, Ashton Carter. So Secretary Carter at the time wrote, to realize improvements, the Department of Defense systems must become more spectrally efficient, flexible, and adaptable, and DoD spectrum operations must become more agile in their ability to access spectrum in order to increase the options available to mission planners. We must have spectrum access when and where we need it to achieve mission success. So what I'm talking about here is really a little bit more than just a paradigm in how you put systems together, but it's the way that the warfighters can adapt quickly to different threats across the globe, right? Doesn't matter what kind of conflict we fight anymore, you're going to see that EW is a very important part of that, right? Spectrum access, spectrum dominance will be what we need to defeat any of our enemies, whether it's a peer, near-peer threat or an asymmetrical type threat where you're using just special operation forces, right? So that's what OpenRFM is trying to help accomplish, right? And that Lego building block approach is kind of where we're looking to go with that, right? So that's kind of the brief talk. It goes into, I know I went into a lot of the whys. If you guys want to catch me in a break, I can get into the whats and hows of how we get down to that. I hope it was informative. I hope it's a little provocative. It's a little bit different way of thinking, especially from a systems perspective. But, you know, it is something that we need to enable and help the DOD enable to actually protect the warfighters and actually protect all of us as well.